Alright, so section 6.2 is on dealing with what are called inverse functions, and we want to do three things. Number one, answer the question, what is the inverse of a function? Obviously you can't do much with it if we don't know what it is. So what is the inverse of a function? How do you find the inverse of a function? How do you verify that two functions are inverses of each other? Those are our three tasks. So first of all, inverse is a fancy word for opposite. Inverse just means when you're talking about functions, in functions you have an x and a y, and inverse means you flip them around. So if you look at these coordinates right here, what's the inverse of that function? Well, if I swap 1 and 5, I would get 5 and 1. If I swap 2 and 6, I would get 6 and 2. If I swap these coordinates, I get 7 and 3. Those are now inverses of each other. It basically means that you just switch the x and the y's. The domain of the first one becomes the range of the second. The range of the first one becomes the domain of the second. Okay, this says we have this function 1, negative 2. So I'm just going to graph this. There's 1, negative 2. 2, 5 would show up right here. And 4, negative 1 would be right here. It says the vertices of that triangle. So here's the triangle right here. And point A, just put this in order. So there's point A, there's point B, there's point C. Find the inverse. Okay, so the inverse just means that we flip them. So the inverse of this point would be negative 2, 1. I'm just going to flip that. Negative 2, 1 is here. That's going to be A with that little negative 1. That's the symbol for inverse. The inverse of that would be 5, comma 2. So 5, 2 is right here. That would be B inverse. And then the inverse of this one would be negative 1, comma 4. Which is right here. So that's C inverse. Okay, so now we get this, and what we'll notice is this is kind of like reflected around that line right there. That's the line x equals y. It's like a perfect reflection of each point around the line y equals x. Why does it reflect around that line? Because if you swap the x and the y, you get x equals y, which is really the same function. So that's how you graph the inverse of that, and that's what it looks like. A little bit better picture than mine. Okay, here are the symbols or the notation. This is the symbol f with that little negative 1. It means f inverse or the inverse. It does not mean an exponent, so that's often what confuses people. So if this is our function, that's how you write the inverse of the function. Okay, here's basically what that means. It means if I plug in a to this function and get out b, that means if I swap them, if I plug in b to its inverse, I should get out a as a result. So let's just test that pretty simply. Let's suppose this is our function. If that's the inverse, let's test it. Okay, so f of 6, they're showing us down here, f of 6 means if you plug in 6 there, you get 6 minus 4, which is 2. So now I should be able to plug in 2 here and get what I started with, get 6. And in fact, 2 plus 4 does equal 6. So those are inverses of each other. But that's not the proof, but that's a way to show, at least that it works in one case. We'll show how to actually verify it in just a sec. Okay, this is a great picture that I want to show. So what do inverses do to each other? Basically, if you take something and you plug it into a function and then you compose it with its inverse, you plug that into its inverse, it's like you never did anything to it. So they say a picture is worth 1,000 words. If you can remember this picture, you'll remember what inverses do. If you take x, whatever x happens to be, and then you staple it and then you unstaple it, what happens? Well, you wind up back where you started. Okay, so here's what basically happens. If I take f of x and I plug it into its inverse, those will undo each other. I'll get x, and the reverse is true too. If I take f of x and I plug it into the other one, it will also. So that also works for the other direction. So if I take f inverse and I plug it into f, those will also undo each other, and I'll get x again. All right, here's what it looks like on a graph. So we talked about for a function. Something called the vertical line test. And the vertical line test means this. It means if I can draw vertical lines through this graph and it never touches the graph more than once, then that's a function. Okay, because each vertical line represents an input, and each input on a function can only have one output. So one vertical line can have one meeting point. The way to tell if it has an inverse is it needs to pass the horizontal line test, which means if I put a bunch of horizontal lines through, each of those outputs has only one input. So it's what's called a one-to-one function. A one-to-one means one input leads to one output, and the reverse is also true. One output leads to one input. So this one is the vertical line test, that's VLT. This one is the horizontal line test, HLT. Okay, so for example, this one right here, although it's a function, because it passes the vertical line test, you can see it does not pass the horizontal line test. It's hitting, looks like 4 different times. So that one is not going to have an inverse. Okay. So let's find the inverse and let's then graph it so we can see what the graph looks like. So first of all, how do you find the inverse? We said the inverse means you switch the x and the y. So f of x is the same as y. This is our function. Okay, the inverse is symbolized this way. The inverse is going to be just swap these right here. Oops. So if I swap those, I'll now have x equals 2y minus 5. And then we just want to solve this for y so we can get the inverse. So we have x plus 5 is equal to 2y. We'll divide both of these by 2. That's a 1x over 2, so that's the same as 1/2 x plus, and this is the same as 5 over 2. And instead of writing y, I'm going to write f inverse, because that's the normal symbol, f with that little -1. So here's this function, let's graph that. There's a y-intercept at 2.5, that's the same as 5 over 2. And then the slope is 1/2, so go up 1 over 2. And here's what our f inverse line should look like. So this is the line of f inverse. And we said before it should be winding up to be symmetrical. It should be kind of reflected over the line y equals x. So here's our regular function. 2x minus 5 has a y-intercept of -5 and then a slope of 2. So go up 2 over 1, up 2 over 1. So let's see, did I do that correctly? I think so. Up 2 over 1, it looks right. And so we wind up with this right here. That's not a very good line, but you can see it is kind of symmetrical around this line right here, around the line y equals x. If I had drawn it straighter, it would be more obvious. But this is the line y equals x, and if something is an inverse, it will be reflected or symmetrical over that line. Notice that both of these lines pass both the horizontal and the vertical line tests. In order for something to have an inverse, it has to pass the horizontal line test. It has to pass the vertical just to tell if it's a function. It has to pass the horizontal for it to be a one-to-one function. Okay, so this one right here is actually the next one they're going to do is not technically going to have an inverse, and we'll see why. So first of all, how do you graph this? This is going to be a parabola. It has a y-intercept of 1, and then it's basically just a parabola that's been shifted up 1, so that looks like this. Okay. Here's the problem. Notice that that's going to fail the vertical. It passes a horizontal line test. It's going to fail the, other way around. It passes the vertical line test, but it's going to fail the horizontal line test. That's hitting twice. So this actually technically doesn't have an inverse, but we can still solve for it and just see what it looks like. Anyway, so here's how you find the inverse. Okay, here's how you find the inverse. So we're going to swap the x and the y. So the original one was this. Now we're just going to swap these. So we get x equals y squared plus 1, and we want to solve that for y. That's how we find the inverse. So x minus 1 equals y squared, square root. And then here's the problem. We have to put a plus or minus in front. So the reason this doesn't have an inverse is because it's really like two different functions, and you can't really graph two functions on one. So the square root of x minus 1, we'll talk about how to graph that later on, but it's basically going to look like this. And the negative square root of x minus 1 is like that. So you can see they are kind of symmetrical around this line, but in theory, it would be more correct to say that doesn't really have an inverse. You can't really, here's a better looking picture. You can't really do that because they tell you right here, it does not pass the vertical line test. This is not even a function right here. And that's because the first one was not a one-to-one function, did not pass a horizontal line test. That means its inverse is not going to pass, or its pseudo-inverse is not going to pass the vertical line test. Alright, the last thing I want to show you is how do we tell if two functions, so we know how to find inverses, we switch the x and y and we solve for y. That's how you do it. How do you tell if two functions are inverses? And we kind of already saw that with that staple and staple remover question. Here's how you test if they're inverses. If f of g, if I plug in g to f and it cancels out and I just get x, and if the reverse is also true, if I plug in f of x to g and I just wind up with x in both cases, it has to be both cases. If either of those don't equal x, then they're not inverses. If both of their compositions, because that's what this is called, f of g and g of f, those are called composing, or the composition functions. If both of them equal x, and only if both of them equal x, that's the way that we tell if they're inverses. let's do that right here. Let's try this one. So we need to find f of g, and we also need to find g of f. And they both need to wind up only equaling x. If they don't, they're not inverses. Alright, so let's start over here. So f of g means f of this function. And that means wherever I see an x right here and I see an x there, I'm going to plug in that g of x function. Okay, so let's distribute the 3. 3 times a third is just 1x, and 3 times negative 3 is negative 9. Negative 9 plus 9 is 0, so at least it works for the first one. It does equal x. That's what we want it to happen if they are inverses. G of f of x means g of this function. That's f of x. And that means wherever I see an x right here, I'm going to plug in 3x plus 9. And then we still have that minus 3 right there. So 1/3 of 3x is x, 1/3 of 9 is 3. We still have that minus 3. Those cancel, and we're just left with x. So that means, what does that mean? It means f and g are inverses. Okay, explain the reasoning. When we did our composition, in both cases we were just left with x, and that's how we tell if they're inverses, if they kind of undo or cancel each other out. So let's test out this one, f of g of x, and we can kind of already tell this is not going to work because we know x squared doesn't have an inverse. So we do this correctly, it should work. So f of g of x means f of that. That means wherever I see an x, I should put, now they might be defining these to be inverses, kind of like they did in the last problem. I mean, different books will use different terminology. At least in theory, x squared should not have an inverse because it's a parabola and it fails a horizontal line test. So 2 root x squared, well 2 squared is 4, and root x squared is just x. So 4 times 4x is 16x, and that does not equal x. So we don't even have to do the other one. It already fails the test. The other one, even if remember, if one of them works, it doesn't matter. It needs to be both of them work. So that is 6.2. We talked about what is an inverse, how to find inverses, and how to verify if two things are inverses.